Good morning, everyone. Welcome to the one additional episode of the CINE webinar promoted by CINE. And today you have a pleasure to have a very important speaker here with us, this Professor Mathieu Salanne. And before to move to that, I would like to say some few words about CINE, but I will give this pleasure for one of our faculty members that his work on CINE, he is a faculty member in the Unicamp, and his work on the experimental on supercapacitors. And then I would like to invite for the stage now Professor Hudson Zani to say some few words concerning his work on the experimental focus on supercapacitors. And then is a work that has been done and have very important publications that happened the last years. Professor Hudson, I just provide the words for you. If you could tell us what you have done in CINE for the last 3 years on the focus on the supercapacitors. It's my pleasure to have you here.
It's my pleasure. Thank you very much, Juarez and CINE, for the invitation. Today I'm going to talk a little bit about supercapacitors and what we have done here in ACS division in this term. So first of all, when you look for general people say, when you look to the outside of the cell, capacitor and battery look like the same. But when you see intrinsic properties, the materials, the energy storage process, the intrinsic process, and the features of the materials are completely different. For instance, the equivalent series resistance of a supercapacitor is much smaller than a battery. The voltage you see here in this graph here, the voltage drop or up very strongly and quickly in the supercapacitor, and the battery did remain very constant, almost the same voltage. So the supercapacitor is a device that charge very quickly and discharge very quickly. We can have lots of cycles, and you see the energy and the power of the system are very different. So they're let's say a complementary device. So let's see what we have been doing here in CINE, in the AES division, for this device. So we have been studying this the main three process for energy storage on the supercapacitor. The adsorption process in the surface of a high surface area carbon material, also the pseudocapacitance from redox process or intercalation. How we do that? We do that by developing materials and device. So basically we produce several different types of carbon-based material, like graphites, graphene, nanotubes, activated carbon, and all others materials. And also we decorate this material with metal oxides or polymers to have pseudocapacitance. I'm just put here very quickly an example what we have been doing. So we are, most of us engineers here with some feed on electrochemistry. So most of the experiments we do in a coin cell. And this here is an example where you put all carbon material in a positive electrode for example, nanotubes with activated carbon. And then we have in a negative electrode nanotubes wrapping niobium pentoxide. So we have asymmetric system, for example. And we do a lot of characterization on the system, CVs, impedance, chronoamperometry. So we have been in study and discussing the literature some misleading data. For example, the work window voltage on the aqueous electrolytes. Some case they're in abuse regime, but showing as a working voltage of a supercapacitor, a very large voltage. And that's some mistake we have showing the literature that's wrong. We have try to separate some batteries from supercapacitors materials and show, for example, in letter G, for example, we have an example of the device I show, and we have a triangle shaped charge-discharge material. We study distributed capacitance, we study impedance of the device a lot. So basically, in very short, and I make a draft by my hand here, just to show the students and everybody that are listening us today that supercapacitor, if you have a supercapacitor in the impedance Nyquist plot, for example, like the scratch I make here, you should have a straight line up. That's the way a supercapacitor works. So we have, if the supercapacitor is perfect, we have the angle phase minus 90 degree or close like the batteries. We have almost two semicircles with 45 degree or something like this on the phase. So we can combine materials, and we have combined and we have performed pseudocapacitors that have some properties like battery, larger energy storage compared to conventional capacitors, but also with some more power than a conventional battery. So that's the niche or the way we try to produce the device here. And we try to do that in two ways. We study this by preparing coin cell and making a pound cells, and we study large cells like this, and we are moving to produce some modules and in the more application manner. For example, this is an example here of our manufacturing. We produce coating, and then we cut, we dry the cell, cut, we make assemble the coin cell, the pound cell, for example, and that's the way we do it. And we prepare models, and we are moving to produce these models, and then put inside a car. For example, here an example where we mix the fuel cell with a battery and supercapacitor to produce a new generation of ethanol-filled car in Brazil that's going to produce electricity inside, and we do not need to use a grid for recharging batteries. We have been working quite a lot on operando characterization and a more fundamental look of this device. We have done some XRD synchrotron analysis of the electrode under dynamic conditions under operando, and FTIR analysis and Raman analysis of the device. So I'll just give you guys an example very quickly here what we do. So we have a similar setup to the coin cell, but we have like this special cell here, L cell, and then we apply voltage, and we see the change on the Raman spectral during the charge and discharge. So in this case, we can see change on intensity, change in shift in the peak position, enlargement of the peaks, a new peak appearance, and all this kind of stuff. And this is a way to prove, for example, intercalation process, a pseudocapacitor intercalation process on supercapacitor. And that's just an example what we have been done. This here, just a zoom in the charge for you guys to have a better look, and in the discharge process. So that's very quickly in 5 minutes what we have for a little bit more than 5 minutes. Sorry about this. What we have been doing here in the energy storage device or energy storage division when we are looking supercapacitor. So,
okay. Also, thank you very much. I think it was very exciting to be here with us, and by sure we want to have opportunity in the future to invite you for a more extended talk. Okay. I have been very thankful for you. I think it was very nice to show what CINE is doing on the supercapacitor business, because it's a way where we want to go. And for that, beyond of that too, now I would like to invite to the stage Professor Leonardo Siqueira. He's a faculty member of the Unifesp, and I will give the honor for Leonardo to introduce Professor Dr. Mathieu Salanne. The reason is very simple. Professor Leonardo Siqueira has been working with Professor Mathieu Salanne for many years, with several publications on the use of molecular dynamics to address the problems of capacitors and energy storage in general. Leonardo, the word now is with you. You will stay on the stage, and welcome to our CINE webinar.
Okay, thank you, Juarez, for the nice words. For me, it's a good pleasure introducing Professor Mathieu Salanne. But before introducing him, I would like to say good morning, everyone. Professor Mathieu Salanne is professor at Sorbonne Université in Paris and a junior member of the Institut Universitaire de France 2020 to 2025. He graduated in chemical engineer from Chimie Paris Tech in 2004 and obtained his PhD in 2006 at Sorbonne University. His research focused on the modeling of molten salts for energy production and ionic liquids for electrochemical storage of energy. He has published more than 140 peer-reviewed journal articles. He currently holds an ERC Consolidator grant for Project Ampere, accounting for the metallicity of electrode and the polarization of electrolyte and redox reaction in computational electrochemistry. He's a member of the editorial advisory board of the Journal of Chemical Physics and of the Scientific Steering Committee of PRAS, Partnership for Advanced Compute in Europe, funded by the United Europe. I first met Mathieu in Edinburgh, Scotland, in 2007 during my postdoc. I would say that that time was the beginning of the work conducted by Professor Mathieu that was published in Nature in 2012. And this publication, they provide a clear explanation by the performance of supercapacitor built with porous carbon materials by means of computer simulations. The next papers in this issue have also been important for supercapacitors community. As a recognition of this effort, in 2014, Professor Mathieu received the UPAC Young Scientist Prize in Computational Physics for the development of methods to allow realistic atomistic simulation of molten salts and ionic liquids in situations of relevance to electrochemistry. However, before all this recognition, he had been in Brazil twice at Federal University of São Paulo. The first one was in 2010 and the second in 2013. In this last visit, he delivered a talk to Brazilian Chemical Society in annual meeting. So thank you, Mathieu, to be here, and it's a pleasure to me to see you again, and the word is all yours. Thank you.
Thank you very much. So it's a big pleasure to be here today. Of course, I would have preferred a lot to be with you on site in Brazil, and I remember we had a very good time the last time I came here. So I think we can now share my presentation, Marcelo. Yeah. So if you can share my screen, good, and I will put it. So yeah, so I'm very happy to talk to you today about our work on supercapacitors, and we had a very good introduction by Hudson on practical aspects, and you will see that I will be more on the theoretical aspects and how they work, and I think it's very complementary to have these two approaches. But first, let me start by introducing my university, so bring you a part of Paris into Brazil. So my university was created a very long time ago in the 13th century. At that time, it was called Collège de Sorbonne. And for a very long time, it was the only university in Paris. Then in 1971, it was too large. So it was split in certain parts. And my university was called Paris 6. We all are numbers. Then it took the name of Pierre and Marie Curie University and became the largest university in France. And 2 years ago, or now 3 years ago, we reunited with the humanities. And now we are back to have this name Sorbonne University, which is our old name, in fact. And you can see on these two pictures, two aspects of the university. On the left, we have the old Sorbonne, which is a very old building in Paris and very nice to visit. And on the right, you have the view from the Science University, the tower. And you can see that it's a very good view, a very nice view. We see a lot of Paris. And well, hopefully we'll be able to meet again either in Brazil or Paris to enjoy such views and so on. So now let me move on to supercapacitors. And I will, as you can see, I share a slide with a previous speaker. And I think it's a very important one because it's always good to see the difference between a supercapacitor and a battery. And in fact, the difference lies in the decoupling between power and energy. And I like to make a sports analogy to this. In fact, supercapacitors are like Usain Bolt. They are fast, and but they are only working on a very short time. So let's say few seconds, few minutes, while batteries are marathonians. So with a battery, you will be able to do a lot of kilometers, but at a much smaller pace. Another aspect, which was also addressed in the previous talk, is the fact that, when you do fast runs, you can recharge and rerun again several times in a day. While when you do marathons, you need several days at least to rest and to restart another marathon again. So that's another difference between batteries and supercaps. That's in supercapacitors, you can do a lot of cycles, while in batteries, you will be a bit limited on that side. So I think both are complementary and both can have the place in the future of energy storage. And it's also possible that in the future they will be mixed to have a common performance. So now, contrarily to what was presented before, I will now switch to smaller scale. So in fact, we are interested in seeing the electrochemical device, but from the atomistic point of view. So we want to see how the molecules move, how they adsorb into electrodes, and how the device operates. And in fact, there are two important quantities, which is the energy density and the power density. And you have three important factors. The first important one is the capacitance, that is written C in this equation. Then you have the voltage, which is U, and then you have also the resistance, which is R. And in fact, U and R are properties mostly due to the electrolyte, so that they can be optimized separately. But C is very important, and C depends on the interface. And so it's the most difficult one to address, because you need to understand both the surface and the liquid and how they interact together. And this is why I will mostly speak about the capacitance today when talking about these electrochemical devices. So this capacitance, it depends on a lot of factors. So you've seen several structures, you have seen carbon materials, you have seen oxide materials. And in fact, there are billions of possibilities. You can change the surface area, you can change the pore size, you can change the ion concentration, the electrolyte, you can change a lot of things. And so this is a very large parameter space. And our objective is to narrow it down in order to find what are the good conditions that will make a good supercapacitor without testing all the possible material independently. So we want to bring some understanding and also to provide some prediction to people doing experiments in this device. However, there are several difficulties that need to be tackled when trying to understand supercapacitors at the molecular scale. The first one is that, in fact, we are dealing with concentrated electrolytes. So we have a liquid which contains a lot of ions. And this is a difficulty because, in fact, when you look at electrochemistry textbooks, you have this Gouy-Chapman Stern picture of the interface between an electrode and a liquid. But this picture only holds when you have very dilute electrolyte. And even this picture which I show here is wrong. When you start to have such a concentration of ions, it doesn't work anymore. And you start to have very strong interaction between the ions, and you cannot use a simple theory anymore. And for example, you can see there is a large body of work which was made by Alexei Kornishev from Imperial College in order to account for the higher concentration in more complex theories. Also, so 2007, more or less when I started to work on this project, as was said by Leonardo, is the moment where other people started to work on ionic liquids at interfaces. And this is an interesting work by Ruth Lindenberg in Cambridge. And she showed that even if you charge your surface, you don't end up separating easily the ions. And the reason is because they like each other a lot. So cations like to stay in the vicinity of anions and vice versa. And so it's very difficult to understand the structure because you have these strong correlations. Then the second important factor is that we are dealing with porous materials. And so you have to understand confinement. And so one of the important starts of our work was an experimental study by the groups of Patrice Simon and Yuri Gogotsi. And these guys, in fact, made a very interesting study where they started from titanium carbide and used chlorination. So when you chlorinate your titanium carbide, you end up with a gas phase of titanium tetrachloride that ever goes into atmosphere. And you have a porous carbon, which are the structures that I show here. And they showed that by changing the temperature at which a reaction is made, you change the pore size of your carbon. And so when you are at high temperature, you have pores that are on average at 1.1 nanometer. But if you do it at a much lower temperature, 400 degrees or 500 degrees, you have pores that are at 7 angstrom. And these sizes are very important because they are similar to the size of the ions. And so you have very interesting effects that start to occur. And in fact, you start to have confinement effects. And so you are not anymore limited by the surface, and you start to trigger new charging mechanisms. And for this reason, they were able to obtain larger capacitance. As you can see here, the specific capacitance, for example, could reach 140 farads per gram. And this is more or less 50% more than what was available before. And so this was the beginning of our story, and we tried to understand this effect by molecular simulations. So at that time, more than 10 years ago, we started to look at this problem. And in fact, in simulations, you have several ways to represent a problem. And in general, when you are at the atomic scale, you either try to represent electrons explicitly, you are in the quantum world, and we do what we call ab initio simulations. But when you are looking at liquids and when you are looking at ionic systems, the time scales are too large, and you cannot simulate them easily using these quantum mechanics. So you have to use classical mechanics. And so to represent this problem, Sipman and Sprigg proposed an approach in which the quantum mechanics problem is simplified a lot. And just by allowing the charges inside a metal to fluctuate, they proposed an approach to have constant potential electrodes or constant potential materials. And then Paul Madden, who is a guy who was hosting Leonardo and me at that time in Edinburgh in 2007, proposed to apply it to electrochemical system and to have two electrodes with different potentials and study the double layer like this. And this is the point where I took over this kind of studies. A problem is that these simulations were very costly at that time. Now we do better, but at that time our code was not very efficient. So we decided to simplify a bit the liquid, and to do this, we use what we call coarse-grained models. So you have here an example of ionic liquid, the butyl methylmidazoleum hexafluorophosphate. And in order to have faster simulations, the cation is represented using only 3 sites, the red balls that you see here. The anion is represented by 1 site only, and for example, acetonitrile molecule can also be a bit simplified, but not as much as the ions. And all these models that we used were shown to reproduce well the thermodynamics of the system. So we know that they are good models for the ionic liquid. Of course, they are not perfect because they don't have all the atomic details, but we know that they are good surrogates of the system. So now, once we add these tools, here is an example of the first simulation we've made. So this is a supercapacitor with carbon electrodes that are 0.5 volts and minus 0.5 volts. And you see that during our simulation, the liquid is moving. And in the meantime, we can also see how the charge is accumulating inside the electrode. So you can see here on the left that you start to have positive charge. On the right, you have negative charge. So this is the red and the green colors inside the electrodes. And well, since then, we have been working with these models trying to improve them and trying to understand what's occurring. So as you can see, we have, during the simulation, we have access to the charge fluctuation. And so in fact, we use this as a response. So this is something that is not very difficult, would be very difficult to have access from an experiment. So we change the potential of the electrode and we look how the charge is changing. And from these changes in charge, we can have a lot of different answers. So this is something really interesting because we can now link the charge inside the electrode to the behavior of the liquid, and we can see whether some structural arrangement inside the liquid generate a better charge or not. And so we can propose solutions to improve capacitors like this. So in this work, I will mostly talk about 3 types of materials. The first one is a baseline. It's planar graphite, and in fact, it helps us to have a benchmark because it's the simplest system you can study. And then to understand the effect of porosity, we have 2 types of carbon. The first one are carbide derived, so it's very disordered like you see here, but with a very strong porosity, so less than 1 nanometer for the size of the pores. And then we also studied more ordered structures like the nanoporous graphene that you see on the right to see whether the order or disorder of the structure is playing an important role. Then for the liquid, we have studied now a lot of them. In particular, I will discuss the effect of the adding a solvent, but not only, we also have now more studies on more complex ionic liquids. So to start with the effect of nanoporous carbons, I think an important part when we do with these simulations is that we need to check that they reproduce well the reality, and so we need to benchmark compared to experiments. So in fact, it took a bit of time before we could do this, and it's only in 2015, so 6 years ago, that we could really do combine experimental and simulation study on exactly the same system, and it was an ionic liquid dissolved in acetonitrile. And so on the left here, you have the electrochemical response given by cyclic voltammetry. So from this, you can get the capacitance, and the experimental value was 85 farads per gram. And in your simulation, we had a value of 110. So I would say 20% different, which is in general a very good agreement when we do simulation. And we could also compare the resistivity. So this was extracted from impedance, as was shown in the previous talk. The impedance gives access to the internal resistance of the system. And you see, and from simulation, it's also possible to compute this resistivity. And you see that here again, we have 20% difference between experiment and simulation. And this shows that the dynamics of the ions are also well reproduced from the simulation. So this is very important because we are quite confident that our models are realistic. They are not perfect, we know there are limits, but we are quite confident that they give a correct picture of the structure and the dynamics. So then you can also compare with more complex experiments. So here you have a comparison between simulation on the left and nuclear magnetic resonance on the right. So it's not exactly the same system, but the comparison is fair, I think. And you see that when you switch from 0 volt, which is a middle point in each case, and at 0 volt, you have as many ions as cations inside the pores. And when you start to apply a positive or negative voltage, you see that you separate them. You start to enrich your electrode either with cations or with anions. And you see that the numbers are very similar between the simulation and the experiments. So again, I think that at least we have a good qualitative representation, if not totally quantitative. So reinforced by this comparison with experiments, we could then try to analyze further structure and try to understand why do we have the increase of capacitance. And so in simulations, what we have is that the porous system have a twice larger capacitance compared to planar graphite. And the first question is, why is it so? And so first thing we did was to look at the local charge on the carbon atoms. And this is what you have here at the bottom. So you have the distribution of charge in graphite. So this is given by the dashed line. And you have two examples of nanoporous carbon. And you see that this distribution is very different. In fact, in the case of graphite, even if the electrode is positive, you still have some negative charges at some point. While in the nanoporous carbon, most of the carbons are positive and some of them are very positive. You have this very skewed distribution. And this means that some carbon are really important, more important than others in the charge storage. So then we try to, I will skip this, and we try to go further into understanding what are the structures that are the origin of this increase of carbon charge. And in fact, in the same time as us, there was a group of Kornishev who was proposed based on a theoretical study that due to the confinement, you start to form what they called a superionic state. So in a normal ionic liquid, what you will have is that every anion will be surrounded by cations and vice versa because of the strong Coulomb attraction, and also because you have a strong Coulomb repulsion between anions and between cations. But Kornishev model showed that due to the screening of the electrostatic interaction, because you have strong electric fields due to the carbon, you start to have this kind of packing when you can arrange several ions of the same sign to be close by inside the pores. So this was a theoretical model, and which was published in 2011. And in 2012, our molecular simulation gave really similar things. So here you have at the top a snapshot from a positive electrode, and you have some anions that are packed together inside a carbon nanotube. At the bottom, you have a larger pore that you can see is filled with cations. So you really have this kind of superionic arrangement. And it's only in 2017, so 5 years later after the simulation, 6 years after the theory, that by doing X-ray, in situ X-ray with a group of Kaneko in Japan, they were able to show that these arrangements are indeed present in the systems. And in fact, it's seen by these, if you look at the data on the right, you have the correlation between ions inside the bulk liquid, that's the first plot, inside a 1 nanometer pore, the second plot, and inside a very small pore of 0.7 nanometer. And the important plot to look is a blue one because it corresponds to the anion arrangement. And if you focus on the yellow line at around 0.4, 0.6 nanometers, you see that you have a minimum in the bulk liquid. So this means that they don't like to be close to each other. In the 1 nanometer pore, it's still a minimum, so you still have anti-correlation between anions. But in the 0.7 nanometer pore, you start to have a kind of pre-peak, and this pre-peak is clearly a signature of the formation of this superionic state. So in fact, I think this is a very interesting example where we had some experimental studies from in 2006, electrochemistry that was showing large capacitance. It was explained by theory 5 years later at that microscopic scale, confirmed by simulation 1 year later again, and it's only 4 years ago that we had an experiment that could really confirm this picture, that we were on the good interpretation of the results. Then, if I continue with this study, this experimental study, you can see that in fact the structure is changing depending on the potential you apply. And what happens is if you focus on the picture on the right, you have some arrangement of ions that are close by inside the pore, and you see that when you have in the middle, when you have a 0 volt, you have only a few ions that are close by, but if you increase the potential, there start to be a lot of them. On the contrary, if you have a negative potential, then you remove some anions from the system and you start to lose about this arrangement. Now we could also characterize a bit further the structure of the ions inside the pore, and we have introduced a quantity which we have called degree of confinement. And in fact, the difficulty here is that you have disordered structure, so you need to have a structural definition that will tell you whether you're in which kind of pore you are. And so this was introduced by my former PhD student, Céline Merlet. And what she proposed was to look at the solid angle around an ion, like is shown on at the bottom here. And so when you have a few carbon atoms in this solid angle, it means that you have a small degree of confinement. Then you reach some, in the middle, you have an example of an ion which is close to a planar surface. So that's a medium degree of confinement. And then on the right, you have an example of an ion which is very close to a kind of pocket inside the material. And then you start to have a large degree of confinement. And what we showed in the study is that, in fact, when you go towards larger and larger confinement, you start to have larger charges on the carbon atoms. And this is the reason why, for example, in planar graphite, you will never reach the same capacitance as you can inside the nanoporous materials. Then we also looked at the dynamics of this effect, because an important question is, of course, due to confinement, you can expect the dynamics to become very sluggish. And in fact, what happens here also is that the disorder of the structure is playing a role. So at the top here, you have maps showing the charge on the carbon atoms depending on the time of the simulation. So at t equals 0, the potential was null, but then we have applied the potential. And you see that some regions start to be charged very quickly, and some others are charged only after several nanoseconds, which is a long time scale at when we are looking at the molecule movement. And so what we could see is that, in fact, at short time scale, you tend to charge the big pores. And at longer time scales, you will have some exchange of ions between the pores, and you start to increase the number of ions that go inside the very small pores. And this is when you start to have larger charge. But in the end, you still have a large diffusivity. And this is something that we have studied in a further study by computing the diffusion coefficients. And here you have values of diffusion coefficients depending on the potential. So you see that they are of the order of magnitude of 10 to the power -6. And in fact, this is 10 times slower than in the liquid. So dynamics is slower, but it's still high enough to allow fast charging of the supercapacitors. And so this is a very important result, because indeed it means that this nanoporous carbon can be useful in commercial applications. Then the second important question was whether what is the best electrolyte. And in fact, there was a lot of hope that ionic liquids would be perfect electrolytes because they have a large concentration of ions. But the experimental results were not so convincing. So in this study, what we made is to change the concentration of ions inside an organic solvent, which is acetonitrile. And here, in fact, you have a very interesting feature. It's the fact that when you increase the content of acetonitrile, you decrease a lot the number of ion pairs. You switch from 100 in that example to 20. So you divide by 5 the number of ions inside the pores. So you could expect to divide by 5 the capacitance. But in fact, the important is not the number of ions inside. It's how much you can separate cations from anions. And so, in fact, when you apply a voltage, here we are looking at the positive electrode, you see that the number of anions, it goes from the green line to the orange line, so you have an increase. And the number of cations, it goes from the green line to the blue line, so you have a decrease. But the extent of the difference between anions and cations it's always the same. You see that in the pure ionic liquid, we reach 125 and something around 90. But in the system where there is a lot of solvent, we reach 50 and 10. And so the difference is always the same. And so what happens is that the capacitance will always be the same. And in fact, the story behind this is that in ionic liquids, you have more ions in the system, so you expect this to be good. But it's much more difficult to separate them because you don't have a solvent that allows to split your ion pairs. And so in the end, the capacitance is no better. Then, of course, you have other aspects which are playing a role. As I told you at the beginning, we look at the operating voltage. And in that case, ionic liquids are much better because you can reach 3 or even 4 volts in some cases, while organic electrolytes are limited to something around 2 volts. So the energy density is better, but the diffusivity is much smaller in ionic liquids because they are a bit sluggish, and you can have 2 orders of magnitude difference in the dynamics in the system. And so in the end, the power will be much larger in organic systems. So in the end, the capacitance is the same in all these types of electrolyte, or almost the same. And what is changing is the operating voltage and the resistance. And so in the end, it means that ionic liquids are good when you want large energy density, but acetonitrile are much better, is much better when you want large power density. And then it's up to you depending on the application you target. The other important question we were interested in was on the use of graphene. I guess you all know that graphene became very famous over the past decade. And as all the other fields, people started to use graphene in supercapacitors. And so the question here, is graphene a new Eldorado for supercapacitors? It comes from a roundtable that we had at International Society of Electrochemistry meeting 3 or 4 years ago, because everybody was ending their talks by, oh, now we will try graphene. And so we tried to see whether in simulations graphene was better or not. An important point is that to have a graphene material is not so easy because, of course, you can have some stacking problems that will limit the diffusion. Having porous graphene is not very easy because you have to make holes inside the structure, and so you can also lose a bit of the organization. And so for this reason, there is quite a large amount of discrepancy in the experimental results in the literature. And the advantage of simulation for this is that we are not limited to a given type of structure, and so we can easily have at least perfect structures that we can control for sure. So in that case, we made this simulation box, so it won't help you if you are not doing simulation because you are not familiar with these numbers, but you have to know that we had 40,000 electrode atoms and 5,000 ion pairs. So for us, this is a very, very large system. And it took us quite a lot of time to get the simulations done. And what we did, so you see here, there are some holes inside the graphene. So the liquid can go from one plane to another. And what we did is to change the separation between the planes. So we switched from 7 to 10 angstrom because we know that's a good range we are interested in, and try to see what was the impact on the capacitance in particular. And so the results we had are this one. So let me switch to this. In fact, when you have large pore, well, not so large, but 10 angstrom, you have 60 farads per gram, which is more or less the same as we had with graphite. And so we need to have smaller pores to increase the capacitance, and then we reach 100 farads per gram. If we look at the volumetric capacitance, there is an increase because the density is better. But the systems with small pores, they all behave more or less the same. And in fact, this behavior is because we have a change of structure. When we have small pores like 7 angstrom, we only have one layer of liquid inside the pore, while when we have 10 angstrom, we have 2 layers of liquid. And so in the end, this is why there is a change in capacitance. But then, so we have better performance with small pores, but how does it compare to disordered carbon? And then it's a bit disappointing because you see that the nanoporous carbon I was showing before has quite a larger capacitance, 130 farad per gram compared to 100. So it means that the disorder and the shape of the pore is also playing an important role on the capacitance. So to go further into this, we again looked at the distribution of charge inside our carbon. And so here you see something very interesting. It's the fact that when you have 10 angstrom pores, you have a Gaussian distribution that is at a low capacitance because it's not so good. When you go to 9, 8, or 7 angstrom, what happens is that you switch to the right, so it's good because you increase the capacitance, but you also have a Gaussian that becomes more and more wide. And so in fact, in the 7 angstrom pores, you have some carbons that are highly charged, positively charged, but also highly negatively charged. And that's not good because you just want positive charge. And if we compare this with a disordered carbon, you see that the black line here, it matches well with the red line at large values, but at low values, it matches better with a 10 angstrom case. And in fact, what happens in the CDC, so in this nanoporous carbon, is that you have pore distribution. And so in fact, you can have large capacitance in small pores, but also you have larger pores that allow you to accumulate anion and cations. And so thanks to this, you don't have counter-ions that are going close to the surface. And so you don't have this problem of the negative charges as you have in the small pores of graphene. So in the end, the disorder and more importantly, the pore size distribution are playing a big role on the capacitance. Then an interesting effect that appeared when we looked at this graphene was we observed a very particular arrangement. And this is something that was a bit surprising. So when you start to have this graphene structure, you see that ions of the same sign go in front of each other. And again, this is not so intuitive at first sight because in general, they would like to repel each other. And in fact, what we characterize this further, and you can see that this is a very strong effect. You really have, maybe I will not show it on this picture, but maybe on this one it's better. You can see here on these maps, on the top, you have some maps of anions, and at the bottom, you have maps of cations. And you really see that the anions, they stack one in front of each other, and cations do the same, but not in the same position. And so we were able to interpret this result by saying that, in fact, you have your surface, you put an anion like this, and because of this, you will have a positive charge on the surface, and this will attract another anion. And so this is an interesting aspect of graphene. It's a kind of transparency of graphene that could be used in some device to increase the capacitance. But of course, you need a very high control of the porosity and of the structure of your material to really take full control of this result. So to conclude this talk, I hope it was not too long. Now we have a good idea on the fact that planar graphite is not having a good capacitance, but this was expected. But then in the case of nanoporous materials, having a pore size distribution seems to be very important and to increase the capacitance of the system, and maybe graphene is not so good, or we should be able to have graphene with pore size distribution, which can be quite tricky to do. Then on the side of the electrolyte, ionic liquids are much better for energy density because they have a high operating voltage. But for larger power densities, then it's better to have acetonitrile or another organic liquid because it will increase the diffusivity of the ions and so it will lead to better power density. Now, if I switch to perspective, now we are, for the moment, we were representing a system in a rather crude manner. I showed you some coarse-grained models and some electron models, but we know they are not perfect because we know there are some quantum effects that occur inside the metal. We know that the liquid can be polarizable. So there are several things new features we are currently introducing in our model, and now we have much better model, I think, and we will be able to have atomistic simulations. The other kind of system we'll be interested in were introduced in the previous simulation is a case of redox supercapacitors. So these are supercapacitors in which you will store some charge on surface, but also we have some redox active ions, and so you can have some electron transfer. And then this was shown experimentally to double the capacitance. So this can be very, very interesting from the performance point of view. And so there is a PhD student in the group who is working on this device, but it's a very difficult problem, I would say. And so these are the main directions we are trying to follow now. And I would like to end up this presentation by congratulating all the people who were involved in the study. You can see that the list is quite long. In particular, some people from my group, I presented some work by Clarisse, Céline, Trinidad, and Zuche, who did some the PhD or postdoc with me. It's a long-standing collaboration with Paul Madden, who really started all this by starting the first models. We collaborate a lot with a group of Patrice Simon, so in the University of Toulouse, and Yuri Gogotsi from Drexel, who are the most important people, I would say, in the field of supercapacitors at the moment. And but the experiments were in situ X-ray was made in the group of Kaneko in Japan. And also, well, most recently, the last result I was presenting was from a collaboration with a group of Leonardo Siqueira, with whom we are interested in modeling more precisely the ionic liquids with some atomistic models. And I will end up by thanking you for your kind attention.
Okay. Thank you, Mathieu, for your nice talk. Yeah, we have one question. I think we could have more. João Pedro Aguiar is asking, the superionic state can change according with the hydrate ion size from the electrolyte. The superionic state can affect the electrolyte degradation in water and salt electrolyte in some way?
Yeah, okay. So so the first question for sure. So here we did not have water, but of course, if you have water, it will screen further the interactions. So you clearly have a kind of superionic state when you have hydrated ions. But I would say that the larger the size of the ions, the more chances you have to reach a superionic state. Because if you think of lithium, for example, lithium is very small. And so the Coulomb repulsion between two lithium ions, even if they are hydrated, can be very, very strong. While when you have this imidazolium, even you solvated or not, the charge is more delocalized. So in the end, I think their size will impact a lot this superionic state. Then, in water and salt electrolytes, the degradation, I'm not sure that it is due to superionic state. From what I could understand, there are two reasons why they have degradation. The first one is because the TFSI anion can be reduced. So this is only this is a true electrochemical problem. The second way is that you have water that is also reacting at the electrode. So you form hydrogen and hydroxide ions. So indeed, that's a kind of superionic state because you have a reaction between two anions, hydroxide and TFSI, because the hydroxide can attack the TFSI. So, but I'm not sure it's a superionic state because it doesn't occur inside pores. It occurs inside the liquid. So I would say no to the second question. I hope I answered well to your question.
Okay, thank you. We have more two questions. One of them was made by Abner. I think you can read it. I don't know if. Oh, okay. You can read it and then you can reply.
Yeah. So the difference in capacitance of pure ionic liquids and ionic liquids in solution systems is not large. Would this be the way to build supercapacitors that store more energy without losing power? So, well, yeah, you have to choose. So I would say that, in fact, if you find an ionic liquid that is not viscous, then you will be able to have more energy without losing power. But I'm not so positive about this approach because it seems to me that a lot of ionic liquids combination have been tried, and I've never seen one of them that really gives much better viscosity. So unless someone comes out with a new solution out of his hat, I think it will be difficult to have high power supercapacitors based on ionic liquids.
Okay, thank you. We have more and more questions. That's good. Gabriel Nascimento has another question.
Yeah, so in the previous years, we have been seeing an increase in the number of 2D materials that have been proposed and synthesized. Do you believe that other 2D materials can be proposed for electrodes? So clearly, the main example is MXenes. So you probably heard about them. So these are materials that are made from max phase, so things like titanium, aluminum carbide, and you remove the aluminum, for example, but you have a lot of different other examples, and you end up with 2D materials that have very good conductivity, and they can be swelled quite easily, so you can make them porous and allow the electrolyte to go in between. For the moment, most of the studies were made in aqueous electrolytes, and in fact, it's mostly pseudo-capacitance. So this is more related to what was presented before, because you have some kind of chemical reactions at the surface. But this is a problem we want to study with Leonardo. I think we have a common project on this. So yeah, I believe that other 2D materials can be used for sure. And it's certainly a very exciting field of research.
Good. For sure, we can go back to this talk related to 2D materials. We have to put it to work. Okay. Now we have another question from Guilherme. He asked, what's the difference can we expect if we use polarizable model for both the electrode and electrolyte?
Yep. So indeed, when we have polarizable force field, the advantage is that dynamics will be better reproduced. So I think we will have a better accuracy on the interaction. Does it mean we will have changes in the capacitance? I'm not sure. But we have made the first example. So this is something that we have just implemented in our code. And in one example, we have an increase of capacitance of 25%. Is it a generic effect or just by chance? I don't know. So probably in a few months, I will have more answers to this. I would expect the capacitance to increase because the models, the non-polarizable models, we use some reduced charge, while with the polarizable models, we use integer charges. So at least we should expect an increase of capacitance due to this.
Yeah.
And it should
Okay. I have a complementary question in this regard. Don't you think that the dipole, the induced dipole, would allow closer interaction between the like cations in the superionic state, and then increase the capacitance?
It's possible. It's possible. The thing is that in these ionic liquids, the polarizability is quite distributing along the sides. It's not the same as when you take chloride, for example, because chloride, you only have one ion, one dipole, so you can have some kind of alignment. Maybe in the case of ionic liquids, it will be more diffuse, so I'm not sure we'll see this effect or not. But that's a good question.
Thank you. We have more and more questions. It's very, very good.
I think there was a question on that one, right? Or
it's on chat.
no, okay.
Okay, there is another question from Guilherme, and he asks, what would be the impact of internalization of the electrode surface, such as in reduced graphene oxide and in the zeolite template carbon?
Yeah, so there are several effects that you can expect from reduced graphene oxide. The first is that you will make some defects on the structure, and I think the defects are good because they break the cation and ion arrangement. So this can increase the capacitance. It will also change the electronic structure of the material. So it can play a role of dopant. I think that reduced graphene oxide has a good conductivity. And so this is something that now we are starting to tackle in the simulation. So I don't know what will be the effect, but I think it can really impact. And putting, for example, metallic sites, metallic dopants also can increase the capacitance for sure.
Mathieu, can I ask a question as well?
Yeah, sure.
Congratulations for a very nice presentation. I learned a lot. We are only 2 years old on this field, and we have some contributions, and we learn a lot with reading some computational experiment or computation simulation works that try to bring theory to experimental we performed here, for example. And my question is that we get very excited because we are assembled the center, and at the beginning we didn't have glue box, so we performed lots of experiments on aqueous electrolytes because it's much easier to handle. So we have a learning curve to study. So let's start with the easiest in the, let's say, assemble way, but the explanation is quite hard. And we get so excited with aqueous electrolytes, especially the Ys at the beginning. But the truth is that we didn't get the working window voltage as most of the reports show. And we observed some enlargement on the work window voltage, let's say 1.8, 2 volts maximum, but not that 4 volts we saw report elsewhere. So first of all, do you think that we are not performing the experiment properly, let's say, or there is some misleading on the experimental on this guy's works?
Yeah, I think what you obtain is perfectly normal. What happened is that there was a big excitement about these Ys, water and salt, because of the first papers. But in fact, it's written in the papers, but it was not so obvious at the beginning. these systems are as all battery electrolytes, they are out of equilibrium. And it's only because you are having a solid electrolyte interface, you are protecting your electrode, that you can reach this voltage. And the problem in supercapacitors is that you don't want any degradation of the electrolyte. So with colleagues in France also, we try to use them in supercapacitors, but we never had 4 volt. We had, yeah, as you said, 1.8, maybe, yeah, but not more than this as a voltage.
Can I ask you one more question, please?
Yes.
I get so excited with this superionic states you show, and we start work with organic electrolytes here, and we tested different materials with a different porosity, and we start looking your work right now. So so we start reading this, but before reading some of your works, we bring a theory to by ourselves. Let's say, oh, we may find an explanation for this, and then one thing we start thinking is that maybe this ion, for example, Bf4 minus, get inside a very small porals and exchange electrons. Like intercalation process. I know that is not very favorable, but if you considering that they are pretty close together, and in thinking a quantum level of sharing, let's say sharing electron, I was wondering if that maybe you have some lights on this. Maybe if you have some thoughts. So is that possible? These ions inside the porals could exchange electron, have a charge transfer process, and that will be the reason that you have so higher capacitance. You have a fake capacitance, like a pseudo capacitance in that kind of system, or it's just come up with a first idea we came in mind, and that's no sense at all.
No, I think the problem with all this is that it's always a matter of definition. I mean, when we look at chemical bonds and ionic bonds and so on, we try to separate the stuff between, okay, this is ionic, this is a bond. The thing is that if you had a full electron transfer, then you would have a chemical reaction. So in the end, you would end up with a degraded electrolyte. But what is sure is that, and this is something where I join you, is that the fact that you have ions coming so close to the carbon, you are changing the electronic structure of the carbon. So that's something we don't have in our simulations right now. But for sure, you are attracting electrons or holes, and so there is a change in the electronic structure. So can we call this electron transfer? I'm not sure, but for sure there is an electronic structure variation that is also playing a role in this system.
Just to complement why we think about that, because when we perform impedance, for example, in a perfect capacitor, we expect it to have an ideal capacitor. The phase angle I tried to show very quickly here in my presentation is that it's pretty close to 90 degrees. And as far as we go to higher and higher surface area, electrodal, this, even in low frequency, this impedance line go more in let's say 75, 80 degrees. And in the extremely high surface area, we saw 65, but not like a battery, like 45 degrees. And that's something that's guide us. Oh, maybe we are having some not only adsorption process, but also we have something else, like some charge transfer or something that some impedance relates to the accessibility of the ion. But normally we saw this in high middle frequency and impedance data.
Yeah, well, when you have narrow pores, for sure you will you start to have features that start to be very, very slow. So The problem is that I cannot really answer you because our simulations, as you could see, they are limited in time. Going towards even the microsecond timescale is difficult, and even the materials we have, they are not perfect. So here I would say that the simulations, they don't have the full answer, and this is where you really, well, experiments like yours can really bring some effect that we won't see in our case, and and I think there's still quite a large gap to explain all the experiments, unfortunately.
Thank you very much for all this, all the knowledge you share.
Thank you.
Okay, so let's continue. Now we have a question from Pedro. Can the conductivity of each ion interfere with the electrode's capacitance?
Okay, so I'm not completely sure I understand the question. So because if it's about diffusivity, it will not really impact the capacitance. It will impact the charging time, because the capacitance is normally a thermodynamic quantity. So it's linked. It will not be linked to the dynamic features. So I would say no to this answer, to this question.
Okay. We have another question from Tuanan. Tuanan asks, what do you think about the use of external electric field to simulate the difference of charge between the electrodes in the MD?
Yeah, so that's something we've worked on recently. In fact, there are quite a lot of studies in molecular dynamics where you just take a liquid, you apply a field, and you look at what's going on. The problem by just doing this is that, of course, you are simulated like an extended double layer, but how much it is representative is I don't think it's very representative to what happens, at least in a supercapacitor. But then recently, what we have made, so this is going to be a bit technical. In the simulations I've shown, we have two electrodes and a liquid in between, and it's two-dimensional. But what we have made recently is to have one electrode only in the middle, so liquid there, liquid there. But due to the periodic boundary condition, the liquid is joined. So we have, in fact, we have one liquid, one electrode, and then we apply the field. And so what's happening is that compared to a bulk liquid simulation, is that due to the field, you polarize your metal. So you have positive charge on one side, negative charge on the other side. And so you polarize also the liquid, and you reach a steady state that is exactly similar to what we had with two electrodes. So it works well. It works well, but it's, well, you have to, there are some technical details that have to be handled. And in fact, this is a very, very interesting, I think it's a very interesting development. I've just put a preprint yesterday. So if you look on the archive, now we are able to do some amperometry. So it means that we are able to fix the charge inside the electrode, the total charge. So we are at open circuit condition, but not the potential. So the potential fluctuates and the charge is constant. So that's another extension that can be done thanks to electric fields.
Okay, thank you. There are a lot of questions here. And our boss here just told me to do only 2 more questions.
Perfect.
So as soon as Tuanan, I have his email address, and also Rafael, I can send you the questions, and then if you could reply it after
Yeah,
it would be great. Okay, so let's go to the question about William. William Spinoza, thank you very much for your very nice presentation. And then the question is here.
Yeah. So, very, very interesting question. So, what's happening is that carbon first allows you to have nanoporous material. It has lightweight, and so in the end, if you take the capacitance per gram or per cubic centimeter, it's much better than other materials so far. Maybe Maxines or others will be good. Maybe MOF will be good. But in fact, if you take metals with a large density of states, so gold, platinum, and so on, then it's very difficult because you cannot make them nanoporous. They will react a lot. They are more reactive. They can also do some surface structural rearrangement. So of course, if we could get a material that is both easy to synthesize in a nanoporous way and with a high density of state, then it would be the perfect capacitor. But we don't have this.
Okay, so just to finish then, I have one question. It's a quite a general question. What would be the future of supercapacitors? Would it be related to electrolyte or new materials for electrode?
Yeah, I think it's it's a bit of a matter of there are some. It's funny after now 10 years in this field. At some point, you think that nothing will be better because you don't see things coming out, and then you have a new material. It's Maxine, so certainly it's increasing things a lot. Then you have a new electrolyte, the redox electrolyte, and you see that something that you did not expect at the beginning. So it's a very tricky question. I think that it's very hard to predict what can. In terms of device, I would say that maybe one future will be to have some mix between capacitors and batteries. So systems with two types of electrode can be very interesting from an application point of view. But then, well, on my side, I think I work on both. I'm interested in both, so I cannot tell which one will be the most important in the future.
I see. Okay, so thank you very much for your time and for your presentation. And now I pass the word for Juarez.
Okay. First, I would like to thank you for the very nice talk and for the insight discussion. I think it was very important for everyone that was have a very large audience. Okay. The video now is going to be available on the YouTube, and then we will try to disseminate it even more if it's important also too for us. And then thank you very much.
Thank you. Thank you. It was very nice meeting you.
Marcel, we are in the YouTube until or no? Marcelo, we can finish the live transmission.